Okay, thank you all for returning after the very fantastic break. Okay, and the good news is, look, we're more than halfway through, so we may not have to go the whole time here. We'll maybe let you out a little early. So where we left off last time is I had first told you there was this sort of, if you have continuous recourse, then there's this easy extension of Bender's decomposition where you just solve an integer programming master problem, and then you go solve the Bender's LP subproblems, and you get your Bender's cuts, and you go back and forth. And that's very easy. But the problem with that potentially was that the master problems might get to be very, very hard that you're solving, okay? And you're sort of wasting work time to time, okay? So then I said, well, let's try a different idea. Let's just do one branch and bound tree and add those Bender's cuts throughout the branch and bound tree. Okay, and that works. It's a little bit more complicated to implement. It's quite a bit more complicated to implement. And we saw an example. And in that example, it didn't look all that compelling that this is a very efficient algorithm, unfortunately. And what went wrong, I think, is poor LP relaxations. So if you think back to where I was giving you this quick introduction to integer programming technology, I told you that we do branch and bound, and you do linear programming relaxations branch and bound, but I also told you that the reason commercial integer programming solvers work really well these days is because they add valid inequalities, they add cuts, right? So if they just do pure linear programming branch and bound, that would be terrible. It's hopeless. And what I just did, where I just added the Bender's cuts as part of the branch and bound tree, that's the analog of just doing pure linear programming based branch and bound. That's not likely to be a very good algorithm. Okay, so we have to improve upon that. Okay, so that's what I'm going to try to show you now is a couple different ways that we can try to improve upon that. And so what we want to try to do is we want to add cuts that are stronger than the Bender's cuts. And the way they can be stronger than the Bender's cuts is because they're going to use the integrality information. Okay, so up to Bender's cuts, ignore integrality information. Okay, so we're going to try to do that. And we can do this in two ways. One thing we can do is just try to add cuts based on integrality information that's known in the master problem. That you can do if you have integer variables in the first stage. And the second thing you can do is you can add cuts directly into the subproblems, and that you can do if you have integer variables either in the first stage or in the second stage, or it can be just one or the other. It works so the second was sort of more general. So let's look at the first of these first. So the idea here is I'm running my Bender's algorithm, and I'm doing this branch and bound tree, and as I'm doing this, I'm building up this master linear program relaxation where I have, or master formulation, where I have these cuts here are Bender's cuts that are used to approximate sort of the linear programming value function of my second stage problems, my scenario problems. And so I imagine I consider this mixed integer set. So I have my variables theta that are representing those objective functions, and I have these constraints kind of defining them. And my x variables, my first stage variables, are mixed integers. Some of them are continuous, some of them are integer. So this is a mixed integer set. It has linear constraints, some integer variables. And so what I can do is try to generate valid inequalities using whatever integer programming technology that I have at my disposal for that set. Okay? And so, for example, I mentioned split cuts was the example I showed you guys. And then there's mixed integer rounding cuts. And by the way, we have a paper where we specifically did that in stochastic programming, and it can work well. You can use Gomery mixed integer cuts. And so this is an approach. And ideally, you would like to have all Bender's cuts defining the set where you have theta s greater or equal to qs of x. But in general, you can't know them all in advance, or it's hard to compute with them. So that's why you just use some cuts that you happen to have found by an algorithm up to some point. Okay, so that's why we're just using some cuts. Okay, so how does this look? If going back to that picture that we had before, where we were solving a master linear program, and then we would solve subproblems and get Bender's cuts. So that's sort of what we had before when we're solving just the LP relaxation by a Bender's algorithm. But now what we're doing is we're adding another sort of cut procedure, which is, again, driven by the master problem. So after having solved the master problem, instead of just solving the subproblem to generate Bender's cuts, I can also take my solution, this theta hat, this x hat from the master problem, and send it to a different algorithm that's going to separate integrality-based cuts. Okay, that's going to separate those split cuts, or those Gomery mixed integer cuts, or mixed integer rounding cuts, whatever you like to try to use. and you separate those cuts and you add those to the master problem. And I'm denoting that with these here. Okay, so just generically, this is what they might look like at iteration t of the algorithm. Okay? So I add those cuts, and what's nice about that is then I have the potential, as long as I have some integer variables in the first stage that can sort of give me non-redundant cuts out of that, I can cut off some LP relaxation solutions and improve my bound. Okay, so that's the first thing you can think of to try to do. Now, in terms of implementing that, so it's not so trivial. It's far from trivial to implement Gomery mixed integer cut separation routine or split cut separation routine. That's something that most people, if you're not an expert, actually even experts in integer programming, have a tough time doing that. Okay, so if I tell you you have to do that, that's not so useful potentially. But there's something that's really easy to do, is to help the solver that you have at your disposal that you're using to solve this integer programming, help it help you. Okay? So what we'll do is, if you add Bender's cuts as part of the formulation that you load to the solver, then the solvers have all that technology built in. They're already going to generate all those fancy cuts for you. Okay? So this is why, and for example, in that facility location problem, when we did this LP relaxation loop and we got our final LP value, 286.5 is what we got. But then when I went I was using Gurobi. When I told Gurobi I have integer variables in the first stage, and I just took the cuts that I had found in solving that LP relaxation and gave it to Gurobi, and it said just process the first node, the root relaxation, which means it's going to do its own fancy integer programming-based cuts on top of that. It was able to bring the bound up all the way up to 326.8, a big improvement compared to the eventual optimum is 352. Okay? And that was basically for free. The integer programming solvers did that for me. Okay, so that was really nice. But the key thing to know, this is a very important implementation detail. It seems small, but it makes all the difference in the world in these types of Bender's implementations, is the MIP solvers, and don't ask me why, but this is just the way it works. When you add cuts in a callback, that's the way you have to add cut if you're going to do it in the branch and bound tree. So that's the terminology. A callback is if you're going to add a cut as part of the branch and bound tree, that's the way you have to do it. So you have to do it in the callback. But if you only add cuts from the callback, the solver is not going to use that information to generate additional cuts on top of that. So what that corresponds to is in this set that I'd like to generate cuts for, the solver won't use any of this. It doesn't know that information. Okay? So, and if you remember the facility location problem, there were no other constraints. It was just they were binary. So there was nothing else. So the solver wouldn't have been able to do anything for me if it didn't have those Bender's cuts built into the formulation. So the takeaway from this is sort of just an implementation issue, but very, very important, is this initial phase I told you when you're going to do it this way, where I first solve the LP relaxation and add these Bender's cuts, and then I collect all those and put them as part of my formulation that I then give to the solver before I start that second phase process. It's really important because that helps the MIP solver help you. It will then generate its own integer programming-based cuts on top of that and can get that improved bound. Okay, and it can make a really big difference. So you have to add them in the callback to get a correct algorithm, but I'll also add them outside of the branch and bound tree. That's the lesson there. Okay. Any questions on that? Okay, so that's the master problem cuts. Okay, so that's fairly sort of straightforward that you could do that. But now I'm going to talk about the other option, is adding cuts in the subproblems. Okay. And this is where you have to do more work yourself. Okay, so this is something that you'll have to do yourself if you want to implement this. And so the idea is to consider the constraints defined by a single scenario in my problem and the first stage. Okay, so I'm defining a set, a mixed integer set. I have my x variables and one set of second stage variables, y. And I have the constraints on my x variables and that one scenario set of constraints. Okay, so you can think of this as like a one scenario version of my problem. Okay. And this is a mixed integer set. And by the way, I have integer variables x and integer variables y potentially. I can have variables in both stages. Okay. Now, I haven't yet given you any algorithm, any cutting plane-based algorithm that can handle integer variables in the second stage. I have to tell you a little bit more about that later. Okay, so that's coming attraction. But whatever algorithm you have, generating cuts based on the integrality information in x and y will be useful. Okay, so this is still a useful technique that we can do, these subproblem-based cuts. Okay, and so the point, why am I looking at just for one scenario? So I only have one set of y variables and one scenario set of constraints here, is I'm going to generate valid inequalities for this set. So those are going to be inequalities that have x and y as the decision variables for just one scenario y. And in fact, I'll also have to introduce the theta s variable, say, for the objective function. But they're going to be valid for just, because they're only using the decision variables from one scenario, I can add them essentially to that scenario subproblem, and then I can apply benders exactly the same way I did before. So I preserve the decomposition structure that I had before. That's the important thing. That's why I'm restricting myself to one scenario here. Okay, so I want to preserve that decomposition structure that I had before. So let's see how this, let's see. Okay, so first, just a little bit of theory. Okay, then I'll talk about how this might be implemented. And let's think about, for example, this case of split cuts. Okay, so this is a very important class of valid inequalities in integer programming. Most known valid inequalities are special cases of split cuts. And so I'm going to consider now two different polyhedral relaxations. So on the one hand, there's this set QS, where here, as I mentioned, I'm introducing this variable theta that is sort of the objective variable for the scenario S. And I have my variables x and y, and I'm first of all going to look at the LP relaxation QS, where I relax those guys to be continuous. And PS is going to be the projection onto just the first stage variables, which is the x and that theta. Okay, so it's a set of x and theta where I could find a y that satisfies all these other constraints. Okay? And so when I'm generating cuts in the master problem space, it's kind of like I'm generating cuts in the space of variables PS, where maybe I take advantage of the fact that I know some of the x variables are integer. But I don't have the y variables at all, so just an x and theta variables. That's what I'm doing when I'm generating cuts in the master space. Now, when I try to generate cuts in the subproblem space, valid inequalities for the set where I consider that these variables and these variables are integer, I have these y variables as well. Okay. So I can imagine, what would happen, what's the strength of the relaxation that I can obtain, and I just do a thought experiment. Suppose that I could get every possible split cut. That's really hard to do, but imagine I could get every possible split cut for this relaxation and for that relaxation. And and this theta variable captures all the objective information. So really, if I had the convex hull of these two sets, they would be the same. But I'm not looking at the convex hull. I can't do that. That's too hard in general. I'm just looking at split cuts. It's an important class of cuts. And what we found is that if you could add all the split cuts to this extended variable space relaxation, compare that to adding all the split cuts in this projected space, the master problem space, that, first of all, it's always at least as good to do it in the extended variable space. And in fact, doing it in the extended variable space can be much better. Okay, we just have examples of that shows the difference can be really huge. Okay. So somehow this class of valid inequalities, split cuts, has much more power when you apply it in this extended variable space. Okay. And that's something that's very useful when we're thinking about stochastic integer programming, because we have a natural extended variable space. It's also, by the way, something that's sort of very interesting and useful in regular integer programming. Okay, so that's something that's being explored more. And so if we can add cuts in the subproblems, it can be effective for two reasons. One is we get that power of this extended variable space that's sort of summarized in this theorem. And the other one is that we can use second stage integrality. If you're doing cuts in the master space, you don't even know that there is these second stage variables, so you can't take advantage of them being integer valued. Okay, so we have kind of two possible ways to get power from these cuts in the subproblem space. Okay. Also, going back to this question, I mentioned here I'm always doing the multi-cut version of Bender's implementation here. Okay. And there's actually a reason for that, aside from I only want to pick one. But it also means that if I'm adding split cuts in the master problem, adding split cuts in the master problem where I do the multi-cut version, where I have a different theta variable for every scenario, versus having just one theta variable for the whole sum, I can get a stronger LP relaxation out of the same family of cuts in the multi-cut version rather than the single cut version. So it matters the way you formulate the problem. Okay. So how would this be implemented? So let's go back to our basic Bender's picture. Imagine we're solving now LP relaxations, and we want to improve the quality of these LP relaxations. So I have this master problem. I have some Bender's cuts in the master problem that I've added so far. And this is my usual linear programming subproblem. So again, I've gone back to where I've relaxed any integrality constraints in the second stage problem. So it's a linear program. I can get Bender's cuts out of that. So I have that's my sort of usual loop, master problem, subproblem, back to master problem. But what we do now that's different is after having solved the subproblem, I will then get a subproblem solution. So I had fixed x hat from the master problem and passed that down to the subproblem. Now I solve the subproblem for some fixed scenario S. And my subproblem solution, let's call that y hat S. Now I'm going to send that down to another algorithm that's going to try to separate cuts for me, find valid inequalities for that set XS, which is the set of variables in x and y space. So that set that I'm trying to find valid inequalities for, x is a variable. It's not fixed anymore. That's a very important sort of distinction to make. It's this set. I'm going to go back to it because I want to really be clear about this. This is the set. X and y are both decision variables. Okay. So I find valid inequalities for this set, and I add them to the subproblem. So my subproblem gets bigger. Okay, add these cuts to the subproblem. Okay. But it's still a linear program. And so because my subproblem is still a linear program, after I've done that, now my subproblem value is going to have gone up, hopefully, because I added cuts. And I'll get a Bender's cut that'll be better than what I started with, that I'll then pass to the master problem. Okay. So that's the process. I get some cuts here. I add those to the subproblem, resolve the subproblem, and then finally get Bender's cuts that'll go to the master problem. Now, what's really weird about this, like for a while, when we started working on this and thinking, it's like, could this be useful for a continuous recourse problem? Suppose I only have integer variables in the first stage. My second stage problem, when I fix x, is a linear program. Right? It seems crazy that I would add cuts to a linear program. But the cuts that I'm adding aren't valid just for x fixed. They have to be valid for that set xy, where x is a variable. So I can still add cuts there, and they will cut off the solution that I might get out of this subproblem, and it can give me value in terms of the bound. And so even if that second stage problem is continuous recourse, this methodology is still useful. Okay. Any questions about that? Yeah?
I'm sorry, I just did not understand that last point.
Okay. So let's suppose that I don't have any integer y variables. Okay. But I have integer x variables. My first stage variables are integer. So the set in x and y space is still a mixed integer set. So I can get valid inequalities for that. And those valid inequalities might cut off the optimal solution of this linear program. Okay. And so after I've done that, then I get a new linear program, and I can add Bender's cuts and bring it back to the master problem. Okay. So how can we generate valid inequalities for that single scenario mixed integer set? Okay. So this is where it might get a little bit hairy to implement. Because, first of all, you can do all those general purpose things that we know about in integer programming. You can do split cuts, Gomer mixed integer cuts, Kvato-Gomer cuts. This is how you could do this generically. Okay? But as I mentioned, those aren't so easy to implement. Okay? So that's, unfortunately, you can't get the integer programming solvers to do this for you. That's the difference between the master problem cuts, right? You could kind of piggyback on what the integer programming solvers already do for you for the master problem. In the subproblem, you got to do it yourself. So that's sort of the bad news, but maybe you can try to do that, or maybe there'll be hopefully some libraries for just generating cuts that you can take advantage of in the future. But the good news is you still have the option to use problem-specific cuts. Okay, so if you know something about your problem, you can add those cuts to the subproblem and implement this yourself without having to know about these general purpose techniques. So let's go back to that facility location problem to see how that would work in that case. And it's very simple in that case. So this was our original sort of feasible region for a single scenario in the facility location problem. And remember, we had these kind of trivial-looking valid inequalities where I just look for every pair of customer and facility location, and I just say that the amount I send from facility I to customer J is at most this constant times xi, where this constant might be smaller than ci because the demand at customer J might not be so big. Okay, so that's where I maybe get some improvement out of this. And so because there's not so many of these inequalities, I have two options. I can try to add these as cuts to the subproblems, or I can just add it to my formulation and make the formulation bigger. Okay. So I'm going to be lazy, and I'm just going to do it that way. So I'm just going to directly add them to my formulation, and I have bigger subproblem formulation. Okay. So let's see how this algorithm changes when I do that. So I'm going to start again. I'm just going to go through the LP relaxation. Okay, so I'm going to solve the LP relaxation using now this subproblem, which I've enhanced with these redundant constraints, these valid inequalities in the subproblem. Okay. So the master problem doesn't look any different. My first iteration, I get the solution 0 like we saw before. But now what's looking different is when I go to the subproblems, this part of the subproblems up here is exactly what I had before. But these down here, and I have to put this ... because there's a ton of them. There's for every pair of customer and facility, I have a constraint that's defined by this solution x hat. Okay, so there's a lot of these. Now, actually, what's really nice in this facility location example is those constraints, x hat is fixed, so those constraints are actually just bounds on decision variables. So those actually you can handle pretty efficiently anyway, but that's just a side point. But imagine, there's still constraints. Okay, so you solve each of these new linear programming subproblems. You get Bender's cuts, just like you had Bender's cuts before. It's just that the linear program that you derived them from is different. It has more constraints in it. And so I do that, and I do that over and over again. So I'll skip all those iterations. I'll just cut straight to the conclusion. We have a bunch of cuts that we've added. At the end of this process, we have this solution, x hat and theta hat. And just as a reminder, when we originally solved the linear program relaxation, we got this value 286.5, okay, and the optimal solution is 352. By having added all those redundant constraints to the subproblems, after having finished this, we get the bound up to 332.4. Okay. And this is just the linear programming relaxation. We haven't added any master problem cuts yet. So now I can do what I tell you you should always do, is load these cuts into your integer programming solver and let it do some master problem cuts for you on top of this. So when I did that with Garobi, they brought the bound up to 350.5 compared to the optimal value of 352. So we've almost solved this problem purely with cuts, just by adding those simple redundant constraints in the subproblems. Okay, so that's an illustration of the possible power of adding redundant constraints or valid inequalities in the subproblems. Okay, so I'm going to wrap up this part, this integer programming with continuous recourse. So remember, the first thing we did was a very simple thing of just solve the sequence of integer programming master problems. Or the other one was this quite a bit more complicated, was this branch and cut method where we added these Bender's cuts and possibly other cuts as part of the tree. Okay. So which one should you use? Okay, so what are the pros and cons of these? So just doing that first one, first of all, it's a huge advantage is it's really easy to implement. Okay, so that's definitely much better. It also tends to solve a smaller number of scenario subproblems, right? Because you're doing a lot of work solving that master problem as an integer program. So you're not asking the scenario subproblems to be solved as often. And so if your scenario subproblems are really hard and complicated to solve, this maybe is the fastest way anyway, okay, best method. But this downside, as I mentioned, is that master problem might start to become the bottleneck if you add a lot of cuts. The other good thing about this is that, because you're just solving those master integer programming subproblems, they're just generic integer programs. You can give them to the integer programming solvers, and they take advantage of all the enhancements they have. So that's a good news. The other approach, this branch and cut, is much more difficult to implement. You have to do this, figure out how to add cuts as part of the branch and bound tree using these callbacks. But it might eliminate redundant work because you're only doing one search tree. And you can get the power of these subproblem cuts, which you just can't get in this method, okay? Because there's no notion of a subproblem in terms of what the solver knows about there. Okay? So those are the pros and cons. I would suggest, of course, try the easiest thing first and resort to this one only if that fails. That's an easy thing to do. Okay. So far, I've told you only about what's probably the easiest problem in two-stage stochastic integer programming is where all the second-stage variables are continuous. Okay, so now we're going to make things a lot harder. And so I'm going to start with the simplest case among that is where all the first-stage variables are binary. So first of all, so now I'm going to say, okay, this is my generic stochastic MIP. Now in my second stage, I may have some integer variables. And so why can't I just apply this Bender's approach there? Is because the second stage problem is a mixed integer program, so I can no longer characterize its value function just by Bender's cuts. Okay, so that's the limitation. Okay, I can't just solve the LP relaxation of this and get Bender's cuts and characterize that. Okay, but, and this is really important to emphasize, the Bender's cuts that I could have gotten from solving the LP relaxation of this thing, they're still valid, okay, and they might still be very useful. Likewise, everything I said about subproblem cuts and master problem cuts that can improve the relaxations that you're going to be dealing with, all of that is still valid and can be very useful in this. Okay, so don't forget about any of the things I talked about there. You still want to do all those things. But what we need to do is figure out how can we enforce that constraint that this theta S variable, which wants to represent the value function of scenario S, really does represent the value function. How can we enforce that? So in the case of a pure binary integer program, where all the first stage variables are binary variables, then there's some sort of an easy thing you could do. It's maybe not the most effective, but you can do it, and it sort of finishes it off for it. And so these are called integer L-shaped cuts. So first of all, we're going to assume we have a known lower bound on the value function in scenario S. For example, maybe all the costs are non-negative and the variables are non-negative, so the lower bound might be 0, often is the case. So it's always at least L. And then you fix some binary vector in the space of first stage variables. Okay, so x hat. Think of that as like a candidate solution, first stage solution. Okay. Then we can show that this inequality is a valid inequality. Okay, so it's theta S. We have these things here are constants. We have this sort of weird function of the binary variables, which if you look at this, I'll sort of try to explain to you why this is a valid inequality, why you could add this cut, is if you look at this function of the binary variables, it's going to be 0 exactly when x equals x hat. And if x is anything different from x hat, it's going to be at least 1. That's what this thing is doing. It's just sort of counting up the differences between the vector x and the given vector x hat. So this value is either 0 or it's greater or equal to 1. So when x equals x hat, this value is exactly 0, and we get theta s greater or equal to qs of x hat, which is exactly what you would want when x equals s hat, right? So it's sort of exactly right in that case of x equals x hat. For any x different from x hat, we have to make sure this inequality is also correct, doesn't cut off any, doesn't give me an incorrect bound for my value function. And so I'll just evaluate this right-hand side there. So that's what this is. This term here, when x is not equal to x hat, is at least 1. So this thing here, which is non-negative, I'm subtracting off, instead of subtracting off more than one of them or one or more, I'll just subtract off one of them. So I make the thing bigger. And then I cancel terms. I get L. And I always know theta s is greater or equal to L. Okay, so this is a valid inequality. And what's more is that argument, when I looked at the case when x equals x hat, it showed that for that case of x equals x hat, it gets it right? It exactly evaluates the value function at the point x equals x hat. Okay. So these cuts, even though I'm going to argue in a second that they're not very strong, they're sufficient to define the formulation. Okay. So if I add these cuts as like I did before when I added Bender's cuts, if I add these cuts in the branch and bound tree, anytime I get an integer feasible solution, I'll get a correct answer in the end. Okay, so these help me finish off the problem. Okay. Okay, so we could do this. We could do either of the two algorithms. We could solve the sequence of MIP-master problems, add these cuts between master problems, or we can add them as part of a single branch and bound algorithm. But they should not be used alone. Okay, so I mentioned the Bender's cuts based on LP relaxation, the other cuts based on integrality information, subproblem cuts. Those are all still valid, and you definitely still want to use those, even if you need these integer L-shaped cuts to make sure that you get the solution right in the end. Okay? Because these integer L-shaped cuts are very weak. Let me go back to it in a minute. Here's what the inequality looks like. So when x is not equal to x hat, this term pretty quickly gets big, and it basically says nothing. So outside of the x equals x hat, this cut essentially does nothing. So if you try to do an algorithm that's based only on those cuts, you're quite likely to have to enumerate every feasible solution. Right? Maybe not quite that severe, but it can be pretty bad. So you really need to combine it with these other cuts. Okay. And so, by the way, this idea of using the LP relaxation has appeared at least in this paper. It might even be an older idea than that. You want to use the master problem cuts and the subproblem cuts. You want to use everything else that you know about that you can as in addition to these integer L-shaped cuts. Okay. Okay, so that was kind of an easy case. We had all the first stage variables were binary, and we could add this this integer L-shaped cut. Now there's many other cases. Like you could have pure integer second stage, pure integer first stage, mixed binary first and second stage. And all of those need some mechanism for enforcing that constraint, theta s is greater to qs of x, when x is a feasible solution to the first stage constraints. That's sort of the key ingredient to finish off the algorithm. Okay. And so, and this finishing off that last key ingredient is the subject of many research papers in stochastic integer programming. So I'm not going to go into the details of all of those. I'm just going to basically kind of give you some references for some of these other cases. And so when you have, again, in that case of having just pure binary variables in the first stage, there's the integer L-shaped cuts, but there's other methods as well that could be used. So, for example, you could use split cuts, and there's some clever mechanism for transferring subproblem cuts from one subproblem to another that have been proposed that can save work in generating those cuts. There's been use of Gomery cuts, Fenchel cuts. Looking for Lewis. I don't know if he's skipping out, but he's here anyway. There's ways you can enforce these things by branching. So that's another method for doing this. It doesn't necessarily have to be only by cuts. And then most recently, there's something called Lagrangian cuts, which you could, if you go to Shabir Ahmed's semi-plenary on Friday, you can learn more about that in the context of multi-stage integer programming. If you have pure integer first and second stage variables, then again, you could use Gomery cuts to sort of finish things off. If you have mixed binary first and second, so all the integer variables are binary, but you could have some continuous variables as well. Then you can use lift and project or split cuts again. You can use the reformulation linearization technique. You could derive disjunctive cuts from a branch and bound tree. So I'm just throwing out words here, but there's all these different cases. If you have just pure integer second stage, but the first stage could be mixed integer, general, then there's sort of a clever reformulation you can do with some specialized branching that would eventually finish off the algorithm. And there's certainly some clever things you can do if you're in the special case of having pure integer, but simple integer second stage recourse. So there's all these special cases. One thing I'll highlight here is that the case of general mixed integer first stage, so the integer variables aren't necessarily binary, and you also have continuous variables, combined with general mixed integer second stage seems, I'm not aware of an algorithm that finishes it off for that case, using this cutting plane approach. The next algorithm I talk about would apply to this, but that's sort of a hole, I think, in research right now. Okay, so that's sort of a big break in the talk. I'm going to now split to describe kind of a completely different approach for stochastic integer programming. So this would be a good chance, if you have any lingering questions about these cutting plane-based approaches, to ask them now, or else you can talk to me after. It's fine too. Yeah. Okay, so let's move on to a different approach, and I'm going to do this one much more quickly. And it's sort of, it's approach based on a different type of relaxation, a Lagrangian relaxation. So it's not going to be based on linear programs and cuts. It's going to be a different type of relaxation. And so let's get into it. So the fundamental idea behind this one is to start out by reformulating a problem with sort of a variable splitting approach. So here's my extensive form of my mixed integer program. I have one set of first stage variables. I have a set of second stage variables, ys, for every scenario. Okay. This is completely general, mixed integer, first stage and second stage. So what I'm going to do first, it's going to look really weird, is my x variables, I'm going to create a different copy for every scenario. Okay, so I had one set of x variables. Now I have a set of x variables, x sub s, one for every scenario. And where the x variables showed up, now I had these first stage constraints. I make a copy of those constraints, one for every copy of my first stage variables. I am going to write my objective kind of funny where I'm averaging over all these different copies. My second stage constraints, I plug in for scenario s, I plug in the sth copy of x variables. And now I have these weird constraints, which enforce what's known as non-anticipativity. That's the fancy word we give to it. But all that's saying is that all those copies that I created should be equal to each other. Okay? So that's just a way of saying that. And there's different ways to do this. I chose one particular way. And so the way I chose to do it is to say that the sth copy should be equal to the average over all the other copies. Okay? And if I do that for all of my copies, s from 1 up to capital S, that forces them all to be equal to each other. Okay? So this, right now, this is just a reformulation. This is the same problem. I haven't relaxed anything. Okay? So it's just a different way of writing the problem. OK, but now what we're going to do is we're going to apply the general technique of Lagrangian relaxation to this reformulation. So if I look at my problem, if I go back to that reformulation, everything here is indexed by s, just s, except for this guy where I have kind of variables mixed together. So if I could get rid of those constraints, I would have a different subproblem for every scenario. Okay, so that's what Lagrangian relaxation is really good for. It's good for getting rid of pesky constraints. So we're going to do that. We're going to relax those pesky non-anticipativity constraints with Lagrangian relaxation. So for every copy of my variables xs, I'm going to have a vector lambda s. Okay, so this lambda, each of these lambda sub i's or lambda sub s's is a vector having dimension equal to the number of my first stage variables. Okay. So this, when I write it just lambda, that's a vector of vectors. It's a really, really big vector. Okay. So I define now for a fixed lambda, I define this Lagrangian problem where I took those constraints, those non-anticipativity constraints, and I put them in the objective with kind of penalizing with these lambdas. Okay, so I move them to the objective. And now if you look at this problem, if I can rearrange the objective, which I'll do in a minute, but looking at the constraints, every set of the constraints had just variables that depend on s and data that depends on s. Okay, so it all decouples very nicely. So I'm going to rewrite the objective. I'm going to use the notation that lambda bar is the average of all my lambda s vectors. And so then I can gather terms in the objective, and I get this new coefficient on the xs variable and the same coefficient on the ys variable. So that's just rewriting the objective. So that's my rewritten objective. I also don't like that I have lambda s minus lambda bar showing up here. And since that lambda bar is being subtracted from everybody, I can actually just assume that it's equal to 0, because I could just do that subtracting after the fact. So as a kind of a normalization, I can assume that that lambda bar is equal to 0, which then simplifies my expression here. That I get rid of that part here. And so now I can write my, I can explicitly expose the decomposition from this Lagrangian relaxation, where this L of lambda, I can evaluate that by solving a separate subproblem for each scenario s, where the dual variables lambda s are sort of the input to subproblem s. Okay? And that subproblem s has these constraints, the constraints corresponding to just one scenario, and it has both a set of first stage variables and a set of second stage variables. Okay? So it's like a one scenario integer program. So each subproblem itself is a deterministic mixed integer program. Okay? So integer programming is a lot easier than stochastic integer programming, but it's still not very easy. So you should be a little bit worried, maybe, that these subproblems are difficult to solve. But there's a lot of recent research and good success in solving deterministic integer programs. So maybe we're happy with solving these things for the size we want to solve. Okay, so we're going to assume we can solve these. Okay. So for any fixed lambda, then by construction, by Lagrangian duality theory, the value, when I plug that lambda in and then I evaluate all those scenario subproblems and add them up, that value will give me a lower bound on the true integer programming optimal value. Okay, so this is a different way of getting a lower bound as opposed to solving linear programming relaxation. So any lambda would give me a lower bound, and the Lagrangian dual says I would like to find a lambda that gives me the best possible lower bound using this technique. Okay? So the Lagrangian dual problem is to maximize over lambda subject to my normalization constraint on the lambdas, that the average equal to 0. I guess there should be a PS in there to make the true average. But subject to that sort of normalization condition, I want to maximize the value of the lower bound that I get. Okay, so we call that the value of the Lagrangian dual. Okay, so how good is this Lagrangian dual? I'm going to talk a little bit, or a fair amount, about how we might try to calculate that Lagrangian dual and optimize it. But first of all, what good would it be if we could optimize it? So standard Lagrangian duality theory tells us exactly this. The value of that Lagrangian dual bound is equal to the value of this problem here. Okay, so this looks like an extensive form stochastic program where remember, x sub s are the constraints associated with scenario s. Okay? So if I didn't have this CONV stands for the convex hull. So I had this mixed integer set, and this CONV returns the convex hull of that set. Okay, that's a difficult thing to get in general, okay, but this is just a theoretical statement, okay, if you could have it. And so if I didn't have that convex hull operation here, this would just be exactly the formulation, the extensive form. Okay? So, but the convex hull of a mixed integer set is actually a linear program, so this is sort of a linear programming bound that would be really hard to compute because I don't know explicitly the convex hull. Yeah. But that's what Lagrangian duality tells me, is this is exactly the value of this problem, where I can replace the actual constraints xs with the convex hull scenario-wise, one scenario at a time. Okay. So what are some implications of this theory? So first of all, well, unfortunately, this Lagrangian dual isn't a strong dual. In general, it might be less than the integer programming value. Okay, so just solving this won't necessarily be enough. But what this theory tells us is, first of all, that the Lagrangian dual is at least as good as the usual linear program relaxation value. Okay? Because the usual linear program relaxation value would be obtained by replacing the constraints xs with just the linear program relaxation, which might not be as good as the convex hull. So this is at least as good as the usual linear program relaxation. And even stronger, I think I tried to convince you about how these subproblem cuts, one scenario at a time, could be very useful in that cutting plane approach for improving the bound, and we saw that in the facility location example. This dual will be at least as good as what you could get using any possible subproblem cuts. The best possible subproblem cuts would define the convex hull. So this is sort of even better than you could do with any of this, or equal to what you could do with all possible subproblem cuts. Okay? So it suggests it's a pretty strong dual. It's a pretty good bound. And empirically, many people have found it is a good bound. Okay? And so in many cases, it is quite close to the integer programming value. So it's a good bound. Okay. But, so we have a nice, really strong bound, or in many cases, very strong bound on the optimal value. But we have to compute it. We have to find the value of this bound. And that means we have to be able to solve this problem where we're choosing the lambda that will maximize that Lagrangian function of lambda. Okay, so first of all, lambda, remember, is high dimensional. Remember, I have a set of these lambda variables for every copy of my first stage variables. So if I have s scenarios and n first stage variables, this is the dimension of lambda. So it's a high dimensional problem. Furthermore, so I'm maximizing, the good news is I'm maximizing a concave function. So that's the good news. But the bad news is it's not smooth. Okay, so maximizing non-smooth functions is quite difficult. And finally, to get a subgradient of this, which is what you're going to need for any algorithm for maximizing this, you have to solve all those deterministic mixed integer programs. Okay, so there's a lot of work involved in just evaluating subgradients. So it is a convex program because you're maximizing a concave function, so that's the good news, but it's really challenging. Okay, so we have to think about how we'll solve this. Okay. So how will we solve this? So the first thing you might do is this is sort of the standard algorithm for solving a non-smooth optimization problem is a subgradient algorithm. So at each iteration in this case, what you'll do is you're given some current values of your multipliers lambda sk at iteration k. You go off and solve all your integer programming subproblems, and you get these solutions, xsk as the first stage solutions. You calculate what really is the average of all those subproblems. So you get this x bar k, which is the average over all of those. And then based on that average, you can sort of check the violation of the constraints that xsk was supposed to be equal to the average. So that's kind of the violation of the constraints that you relaxed. And so this is sort of the subgradient of lambda sk. And so you take a subgradient step. So you started with lambda sk, you have some step size they have to determine, and you move in that direction. Okay, so this is sort of a classical subgradient algorithm. It does converge for proper choices of the step sizes, but unfortunately, proper choices of step sizes is a bit tricky to get. And in terms of sort of practical choices, getting it just right can be really difficult. Okay, so it's very sensitive to the choice of step sizes. So this is not necessarily going to be a very effective algorithm. Another approach, very similar to Bender's, is to use a cutting plane method. Okay? So the idea here is we're going to formulate a master problem where we're going to have these, now again, theta s variables to represent this sort of value function for each scenario s subproblem. So we want theta s to be less than or equal to that, which we can't explicitly handle, so we're going to use cuts to handle that. We have our normalization constraint. And then what we do is we approximate those constraints by solving scenario subproblems to get the subgradients. And we build, this is what the cuts would look like in each iteration. So at iteration k, we might have k different cuts for each scenario. And this would be the form of that master problem. It's a master linear program. And you repeat this process until you can't find any more cuts. Okay, so it's really just like Bender's. But again, you have to solve these mixed integer programming subproblems to find cuts. That's the difference from Bender's. Okay. Okay. Of course, just like in Bender's, you don't just solve a pure cutting plane algorithm. You do all kinds of better things to improve upon that. So there's all kinds of regularization techniques, and I won't talk about them, but I'll just put some references here that these slides will be available after the later, and so you can look at these references, and it's for sure an incomplete reference list, so there's many more to look at as well. But generally, you just try to sort of avoid the iterates from jumping around too much by adding some sort of a regularization term that says, don't move too far from one iteration to the next, and that makes these algorithms converge better. Okay. I do want to highlight this last one. Of all of these, this is the only paper that I'm aware of, actually, that has done this, implemented some of these things and compared them for exactly this case of a Lagrangian dual. Like a lot of these are talking about sort of the Bender's problem, sort of that we talked about earlier. This is doing it for the Lagrangian dual. Okay, so when you start talking about this variable splitting approach, if you're familiar with some stochastic convex programming, you might think about this progressive hedging algorithm, which has sort of, it's derived in a similar way. And so this goes back to Rockefeller and Wetz. And it's a really nice algorithm, sort of a primal dual algorithm. At the same time, you're finding primal solutions and dual solutions to solve this problem. And by the way, it turns out to be equivalent to what's known as the alternating direction method of multipliers, just in case you're familiar with that terminology. So how does this work? At iteration k, and again, this is only for a convex program. So this theory has been developed for convex stochastic programs. So I'll describe it now for convex programs. So at iteration k, we solve this convex scenario subproblem, where it looked just like the previous scenario subproblem, except everything is continuous. But we added this augmentation term, which again is sort of saying, I had my previous iterate x bar k minus 1. I want x to be sort of not too far away from that. Okay, so we sort of regularize in that way. We solve these scenario subproblems, these augmented versions. We get the optimal solutions x bar k for each of those, or sk for each of those. We average. And then we do an update based on that average. So that's how we're going to do our dual multiplier updates. Okay, so where in this case, rho might be a fixed step size would work. So it's a very nice algorithm. It converges in practice quite fast. It's more stable with respect to the choice of the step size. But unfortunately, it's for convex stochastic programs. So what about for stochastic mixed integer programs? So the natural thing you could try to do is, let's still go ahead and introduce that augmentation term, because it does seem like a good idea to keep yourself from moving too far from one iteration to the next. And we're enforcing all of our constraints, but now our constraints include those integer restrictions. Okay, so that's sort of the natural extension. And so this subproblem now is now a mixed integer nonlinear, because we have these quadratic terms in the objective, a mixed integer nonlinear program. Okay? Still, that commercial solvers can solve those now with quadratic objectives, so we can go ahead and say, go solve those, and let's implement this. And unfortunately, there's not convergence theory, because these sets aren't convex, so you can't just say it's progressive hedging, it converges. But it's been used to very good effect in a couple ways. So first of all, and actually there's an earlier paper, I think in the 90s, that I forgot to cite here, but it's been used very effectively as a heuristic. Okay, so you can run this with some choices of the step sizes. You run this algorithm. Eventually, it'll converge to an integer solution that is often a very good solution. Okay, so it can be very effective heuristic for finding good feasible solutions. And more recently, it's been realized that you can use this algorithm. You run this algorithm, and as it's running, in addition to finding a primal solution, it's finding some dual solution. And of course, you could always take that dual solution it finds and plug it into your original Lagrangian dual and get a lower bound that way. Okay? And if you choose well the choice of row, oftentimes it will converge us to a good solution, a good dual solution. Okay? So that's sort of a way you could heuristically use this to also get lower bounds. Okay. But more recently, we've, and I'm going to do some advertising for a talk that will be coming later in this conference. We started thinking about, could we do something more? Could we actually turn this progressive hedging idea into a convergent algorithm for the Lagrangian dual? And so the first thought experiment is to say, well, if we, instead of solving the problem where we had the set capital XS in there, which had all the integer constraints in it, we imagine that we can solve the problem over the convex hull. So that's a convex set by construction, right? So if I could solve that problem, then progressive hedging works. So that would be just fine. If I could solve that subproblem, I can just apply progressive hedging, and I would converge to an optimal dual solution. But the convex hull of this set, of a mixed integer set, is in general difficult to get a hold of. Okay, so that's hard to handle. So what we have as our idea is to actually, instead of solving, when we get to the point of solving a quadratic program, this augmented term, we're going to use an inner approximation of this. And working with an inner approximation is easy to do because you just have a set of feasible points and you just ask for a solution to be a convex combination of those feasible points. So that's a linear constraints that you can add. So if I build this inner approximation defined by some feasible points that I have seen so far, I can use that in this quadratic subproblem and try to drive my algorithm based on the inner approximation. But I need a mechanism to update the inner approximation. I have to add more points into it as I go along through this algorithm. And so it turns out that if you solve one mixed integer linear program subproblem at each iteration, so just the regular Lagrangian dual subproblem, and take the integer point that you get from that and add that into your inner approximation, that's enough to make this thing converge. Okay? So that's sort of how you can do this for mixed integer subproblems. So at each iteration, you solve a quadratic program. That's the one that you're going to use to do your updates. But it's a one scenario one. And you solve a mixed integer linear program rather than a mixed integer quadratic program. Okay, so you solve two subproblems instead of one. But one of them is very easy. It's just a simple quadratic program. And the other one is a mixed integer linear program. So same difficulty as the other one that you had before. Okay, so here's the reference to the talk that'll be on Monday with more details of this algorithm. Okay, so we've now solved a Lagrangian dual. Imagine we've used one of these methods to get a Lagrangian dual bound. But unfortunately, so we have some candidate solutions, say lambda hat. It gives us a lower bound on the optimal value. And when we solve all the subproblems with that lambda hat put in, we get all these subproblem solutions x1 up to xs. But it might not be a truly feasible solution because those constraints that we relaxed, those non-anticipativity constraints, they said all these subproblem solutions are supposed to be equal to each other. They might not all be equal. Okay, so we're not done yet. That's why it's not an exact algorithm yet. So what can we do? Well, first thing we can do is we can just hopefully find a heuristic solution, get some upper bound, compare that to the lower bound that we already have, and if they're already close to each other, then I would just stop. I'm happy enough. I have a close to optimal solution because I have a good solution and I have a bound that shows it's good. Unfortunately, if that's not sort of close enough, then we can apply what's known as the dual decomposition algorithm, where you actually then use this Lagrangian dual within a branch and bound algorithm. Just like what I talked about earlier when I gave the generic branch and bound algorithm, that's basically what you would do, except you're using this as the bound within that algorithm. And this, by the way, is implemented in one of the stochastic integer programming solvers. In terms of a heuristic, when you're doing this approach, there's actually a very simple heuristic that's always an option to use. I've solved all these scenario subproblems, so I get first and a second stage solution out of that. So I can pick one of those, say x hat s, and I fix that, and then I go and solve all the other scenario subproblems with that guy fixed, and I've evaluated the value of that solution, so it's a candidate solution. It's a possible upper bound. And that works if we assume relatively complete recourse. It means that whatever first stage solution that I have that's feasible, it will be feasible for all my scenarios, okay, which is usually a good assumption to have. Okay, so how would branch and bound work if you need to do branch and bound? So I'm in this situation where I have all these primal subproblem solutions that aren't all equal to each other. I'll calculate the average value of all those guys. And so because they're not all equal to each other, that means there will be some scenario in some index I where the value of that index, the variable at index I for that scenario is not equal to the average. Right? Otherwise, they would all be equal to the average if this didn't happen. So I have such an I. And then what I could do, if the variable xi is supposed to be an integer variable, I branch by, if it's integer, I branch by on the one hand saying xi should be less than or equal to the round down of its average, or it should be greater than or equal to the round up of the average. If it's a continuous variable, I just can't do the round down and round up. Okay? But the key thing here is that I may still have to branch on this variable even if it's continuous. So that's another difference from integer programming. Okay? The thing I've relaxed here is not integrality. The thing I've relaxed is that all these variables are supposed to be equal to each other. So in this case, when I branch, I have to branch in a way that tries to enforce that back again. Okay? And so I do this by enforcing, in either branch, I enforce these conditions in all of the scenario subproblems. And because they weren't all equal to the average, because it was infeasible, that means that in either branch, for sure, some of the scenario subproblems will have their solutions cut off. Okay? So we make progress by doing branching this way. And furthermore, if you accept that these guys are equal to each other with some tolerance, some fixed tolerance, say delta, which numerically you're going to have to do anyway, then the algorithm will eventually converge. Okay, so, but you have to have that tolerance. Okay. So that's basically all I'll say about branch and bound in terms of using the Lagrangian dual. I just want to make one last comment about this non-anticipative relaxation approach when you have pure binary first stage variables, because this is something I've seen people do before, is you actually, when you have only binary variables in the first stage, you can get away with fewer non-anticipativity constraints. So instead of having to add all those, for one variable, remember I had to add the number of scenarios, different non-anticipativity constraints, saying each scenario version is equal to its average. If I have, so that's the standard one. If I have a binary variable, instead of having one constraint for each scenario, I can actually do this all with one constraint. So it's kind of magic, but it works because the variable is binary. So this is the one constraint. And so I picked one special scenario, call it x1i, scenario 1. And so if that guy is equal to 1, then this right-hand side is equal to s minus 1. And the only way the sum of the other s minus 1 binary variables can equal to that is if they're all equal to 1. So when xi1 is equal to 1, everybody else is equal to 1. And vice versa. When xi1 is 0, everybody else is equal to 0. So this one constraint enforces all of the non-anticipativity constraints. Okay, so it looks like a really advantage. Instead of having, if I have n binary variables in my first stage, instead of having n times s non-anticipativity constraints, I only have n of them. So it's a much smaller Lagrangian dual problem. Okay. But this is unfortunately almost surely a bad idea. So I tricked you. And why is it a bad idea? Is because the strength of the Lagrangian dual, after you do this approach, and then you solve that Lagrangian dual, and it's a lot of work to solve that Lagrangian dual, even with this approach, because remember, you're still solving those integer programming subproblems. That Lagrangian dual bound can be much worse because you eliminated all these constraints. And so then it doesn't pay off to have done the Lagrangian dual approach if you have a weak bound at the end of it anyway. Okay? So it really, it's really a good idea to stick with the original full set of that's a really hard word to say, non-anticipativity constraints. Okay, so let's see how we do that. Okay, so we're almost done, and I'm just going to sort of wrap up with kind of one last nice thing you can do that improves actually both of these methods. Okay, so this is known as scenario bundling. And so the idea with scenario bundling is we have our set of scenarios, 1 up to s. And what we're going to do, instead of treating them as individual scenarios, we're going to partition them, okay, into subsets of scenarios, which we're going to call the individual subsets bundles. Okay, so we just partition the set of scenarios into these pairwise disjoint subsets that we call bundles. And the idea is whatever decomposition method you're doing, whether it be the cut-based method or the dual decomposition-based method, you treat a bundle as if it were a scenario. Okay, very simple idea. All the algorithms basically go through exactly as they were. And so there's just some references. So let's see how that works in sort of the cut-based or the LP relaxation-based method, just to carry that through. So this is my original scenario decomposition. I had these value functions, these value functions QS for each different scenario, and I solved that. It's one scenario subproblem. In the bundle approach, I create new value functions. I call them, say, Q bar. And instead of having one of them for each scenario, I have one for each bundle of scenarios. Okay? But you'll notice the structure really looks the same. I'm just kind of plugging in bundles where I previously had scenarios. Okay? So structurally, it's very similar. And now my subproblems, in the scenario version, I just had the variables and constraints of just one scenario. Now I have to add up all the variables and constraints for all the scenarios in that bundle. Okay? So I have a set of YS variables for all the variables in that bundle. My objective has to add up all of those costs, and I have the constraints corresponding to every scenario in the bundle. Okay? But I still only have one set of X variables, okay? Because the X variables are still the first stage variables. Okay? So this really looks the same as what I started with, and so we can apply all the methods that we had before, cutting plane-based methods on this. Okay. And so why would you do that? Why do I bring this up? Okay, what might be the benefit of that? So first of all, the cost of that is that those bundle-based subproblems are larger, right? If I have 5 scenarios in a bundle, it's 5 times larger than I started before, so it's not as decomposed as I was before. Okay. So that's what you pay. Okay. But what are the possible benefits? So one thing you might have is you might get faster convergence when you're solving all these relaxations. Because if you have these fewer theta variables, instead of 1 per scenario, you have 1 per bundle, the number of cuts required to converge might be smaller. That's kind of just a heuristic argument, but empirically that might be true. Also, although those subproblems are larger, you have fewer of them to solve, so that's good. If you can solve that big subproblem pretty fast anyway, great. So you have fewer of them to solve. But the most important reason why this could be beneficial is in the case of stochastic integer programming. Remember I talked about these subproblem cuts. And these are subproblem cuts that are based on just 1 per scenario. And the limitation of those subproblem cuts is that they're just 1 per scenario. So that's where some weakness might come in. But when I start combining scenarios together in a bundle, those subproblem cuts that are now valid for everybody in the bundle can become stronger. So my relaxations can be better. Okay, so that's a benefit of bundling in this case. Okay. So the empirical questions you have to figure out in this is, how do you bundle the scenarios together? How big should the size be? And that's just a trade-off, right? The bigger you make it, the larger those subproblems become, but you have these benefits. So you have to find the right balance there. You can also do this bundling in the Lagrangian approach. So the idea here is instead of creating, when I did this initial reformulation where I introduced all these copies of my variables, instead of creating a copy of my first stage variables for every scenario, I create a copy for every bundle. Okay? So previously I had XS, 1 for every scenario. Now I have XK as 1 for every bundle. Okay? So here I have those copied per bundle. I broke these down to write them as constraints per bundle. and have non-insensitivity constraints that just say each set of bundle variables should be equal to each other. Okay? So it's fewer of those. And then we relax those non-insensitivity constraints, and you get these bundle subproblems that will look like this. And so it's similar to what we saw before for the cutting plane-based approach, is the bundle subproblem got bigger. Now we have all the scenarios associated with this one bundle showing up in this one subproblem. So that's the trade-off. You get a bigger subproblem, but fewer subproblems. So we have fewer MIP subproblems, but each is larger. We also have fewer dual variables. So maybe solving that Lagrangian dual problem might be a little bit easier. But again, we might get a much better Lagrangian bound, okay, because of that bundling effect. Okay, so that's the benefit. Okay, so I'm going to close with some parting thoughts. This is my son Cameron with his bright sunglasses on, because I think the future is really bright for stochastic mixed integer programming. There's all kinds of very relevant, very important problems that we're only just starting to actually start to be able to solve. And we've made significant and steady progress in methods for them. But we still have work to do, right? So I think even in the very simple case of continuous recourse, I would say this is not a well-solved problem class. Because if you just look, for example, at current research papers and what are they testing out on, the size of the test instances is often only like 10 to 20 first stage variables, maybe 50 scenarios. It's really, if you imagine what you would need to start applying this in real instances, you're not given much confidence. We're not quite there yet. Okay, so we have more work to do to get to scale these things up. And so that's the end. Let's go enjoy the beach, and thank you for your attention. I want to give some acknowledgments to Merva Baudur, who helped me a lot with the graphics in this, and Shabir Ahmed also shared with me his course notes. And some apologies. I tried to put in some references when there were things that I remembered offhand that were relevant, but it's definitely not a complete reference list. It's not meant to be a survey. So apologies if your work wasn't in this. Any questions? It's been 2.5 hours. I think everybody's ready to go.
Everything's clear.
Yeah, right.
Yeah. Okay. Yeah. If this is not the case, I want to thank you really for this.
Okay.
To the poll.
Thank you.